Today we're going to compare properties of two functions, including logarithms, radicals, and piecewise functions. So on my first set of graphs, we're going to compare, we'll look at two at a time, but I went ahead and did three equations just so we could see an example of what we call vertical shift, where a graph is moved up or down. So again, we're comparing. So let's take the red graph and the blue graph. The blue graph is definitely higher than the red graph. So we can compare in all types of ways. We can look at the shapes. If we compare them by their shapes, the red graph and the blue graph have the same shape. Both of these graphs are bending towards a vertical asymptote that just happens to be the y-axis. If we were in Desmos, let's go ahead and look at one of these. We'll just look at the log graph. If we're in Desmos, this is a really good time to zoom in. We can see that it looks like this graph is going to bend. Let me orientate you. Here's the origin. It looks like the graph is bending, and it looks like it's touching the y-axis, but if we continue to zoom in and pull this over, we get a graph that is just approaching the y-axis but never touching it. So all of the graphs that we're looking at have the same characteristics. They're bending. All the graphs that we're looking at on this particular slide, they're bending. Let me go back to my slide. They're bending and they're approaching the y-axis, but they're not touching it. So again, if we're looking at the blue graph and the red graph, the blue graph is higher than the red graph. We could say the red graph is lower than the blue graph. They have the same shape. They have the same asymptote. And that's happening because if you'll look at the equation, here's the red graph. It's just log of x. The blue graph is log of x plus 1. So the reason that the blue graph is higher than the red graph is because of that plus 1. So the blue graph is actually shifted up 1 unit. All right. Now let's compare the red graph and the green graph. So let's compare the red graph and the green graph. So we could say the red graph and the green graph have the same shapes. We could say they both bend towards the y-axis, which is the vertical asymptote, but don't touch it. We could say the green graph is lower than the red graph. We could say the red graph is higher than the green graph. Okay, lots of different things that we can say. If we look at the equation of the red graph, here it is, log of x, versus the equation of the green graph, log of x minus 1, because you have that minus 1 on the outside. That's, again, what we call a vertical shift or a vertical translation or a vertical transformation. And that's why the green graph is 1 unit below the red graph. So again, comparing log functions. On my next slide, let's compare some radical functions. These are all square roots. I'll show you a cube root of x in just a second, just so you know that radicals can look different based on their index. But on these three particular graphs, they all start at the x-axis. So each one of these, if we find something that's similar, they all start at the x-axis. They all are traveling up and to the right. They're all increasing from left to right. They all have an arrow just on the right-hand side. So this is where they continue forever. They all have an endpoint. Again, like we said, on the x-axis. So there's just one arrow in it. On each one of these graphs, there's just one arrow, and it's to the right. If we compare the blue graph and the red graph, we can say that the blue graph is shifted to the left 2 units from the red graph. We can say that the red graph is shifted to the right 2 units from the blue graph. And if we look at the red equation versus the blue equation, we have this plus 2 going on inside. Inside is a clue that we have horizontal movement. And if it's a positive number that's inside, that's going to move the graph to the left. Horizontal movement is the opposite of what you think. So if it's a plus 2 inside the radical, instead of going to the right, it's actually going to shift the graph to the left. That's why the blue graph is shifted to the left from the red graph. If we compare the red graph and the green graph, the red graph is shifted to the right 2 units from the red graph. If we look at the equations of the red graph and the green graph has a -2 inside, which is a horizontal shift to the right. So again, just comparing some radical functions. Let me go ahead and throw in a cube root for you, just so you know that square roots and cube roots don't look the same. So let's take a look at a cube root. To get your cube root on your Desmos, you got to go to functions, you got to go all the way down, you got to pick that key. Let's throw an X underneath here. So your cube roots are going to look different. They're actually going to have an arrow on both ends. And then we could, go in and throw in another cube root, and we could put that X +2 underneath, and we would get the same exact graph, but it would be shifted to the left 2 units. Same shape. If we compared them, they have different x-intercepts, but this one crosses at -2, this one crosses at 0. The right-hand side of these graphs are both increasing, the left-hand sides are both decreasing, and all that kind of great stuff. All right, on my next slide, I am comparing some piecewise functions. I did happen to make all of these radicals. I wanted to kind of do a combo here. So remember, we have piecewise functions. We can do this with any type of function. It can be linear, it can be quadratic, it can be cubic, it can be logs, it can be anything. What makes it a piecewise is where we go in and we put restrictions on our x's. So we're just getting a piece of the graph. We're not getting the whole entire thing. So if you'll notice on this red graph, let me grab my pen. On my red graph, this is the piece where x is less than or equal to 4. So you have a closed circle here because that's what a square root does. And then it doesn't go on forever. It's actually just a piece of that. On your blue graph, we only want the piece where x is less than or equal to 5. So here's your blue graph. So it ends right here where x is 5. And then it starts on the x-axis. And then I didn't go all the way out to x, but your green graph is going all the way to x is 6. And then less than that. So this graph actually should go up to about 6, maybe about right there, and it will stop. So one thing that we can compare is we have different pieces based on x is where our inequalities are. So the red graph, we only have this piece of the graph where x is less than or equal to 4. The blue graph, we only have this piece where x is less than or equal to 5. And the green graph, we only have the piece of that graph where x is less than or equal to 6. So we can compare it that way. All three of these graphs have a similar shape because they're all square root functions, but they are steeper. So can y'all tell that the steepest is the green graph? If we talked about walking up the graph, physically walking up the graph, it would be harder to walk up the green graph because it's steeper. Okay. The red graph actually is the less steep. It would be the easiest one to walk up. And then the blue graph would be somewhere in the middle. And that's happening because of the numbers that are being multiplied times the square root. That's called a vertical stretch and shrink. So once the number is larger, that's being multiplied times your function. If that number is greater than 1, that's going to cause a vertical stretch. If the number is between 0 and 1, it's going to cause a vertical shrink. And on that red graph, on the f of x, there's actually an understood 1 there. Meant for that to be in red. So comparing piecewise functions. And then my last slide, I think I've just put all three. So I have a log function, I have a square root function, and then I have a piecewise function. I have a piece of a linear graph. So if we look at our log function, it's the red function. If we look at some of its properties, it continues on the right, it bends towards the vertical asymptote, and then it continues to go down without touching that vertical asymptote, even though it looks like it is. So the log function is actually infinite on the left end and the right end. Okay, it's a curve. So if we look at the blue graph, it's also a curve. So the radical graph is a curve and the log function is a curve. That makes them similar. They're both curves. If we look at the square root function, it has an endpoint. It actually starts here at an endpoint, no arrow, and then it continues to increase as it travels left and right. So the square root function only has one arrow on one end, and a log function has an arrow on both ends. And then the green graph is my piecewise function. It's actually a piece of a line. It's the piece where x is less than or equal to 2. So it actually have a closed circle on this end, and it would go on forever and ever because we're collecting this graph where all the x's are less than or equal to 2. So that would go to negative infinity. So this graph would have an endpoint on the right side and an arrow on the left, so that it would be similar to the radical function, the blue graph. There is a continuous slope on all linear functions, so I can go up and over, up and over, up and over, which we call slope, rise over run. That's continuous on a linear function. It's not continuous on a curve. The slope is different based on any 2 points that you pick, so that's a little bit different. So again, just comparing, looking at 3 different functions: a log function, a radical function, and a piecewise function. So today, again, was going over comparing properties of 2 functions, and we did more than 2, but we definitely did 2, including log functions, radical functions, and piecewise functions.